Hey, David. You're welcome to try sharing your screen if you'd like, or we can just do it live. It's pretty consistent.
Let's try.
We can't hear your audio at the moment.
That's a good, okay.
Oh, wait, hold on. That's probably because I'm not wearing my headphones.
Yeah, I can hear it. I can hear you.
Okay. Good to know.
User error there.
Shall I try the screen share then?
Yeah, you can just try quickly share.
I've tried a couple of times already, but it should be.
Oh, wait, did you just do this while I was gone? This always happens.
No.
Okay.
Let's try that.
That looks great.
Cool.
Cool picture.
Okay then.
Thank you.
So I just keep it as it is, or?
Oh, we'll put up the other screen for the moment. Yeah.
Okay. Yeah.
If you don't mind sharing that again, Tracy. Thank you. All right, hello everyone, and thanks for attending today's CGD seminar. Before we get started, I'll remind everyone of our CGD Code of Conduct at these seminars, where we offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. I'll also ask that everyone please keep themselves muted and save any questions you have until the end. If you have any clarification questions, feel free to put those in the chat and I'll read them out as necessary. Now it's my pleasure to introduce today's speaker. Dafydd Stephenson is a postdoctoral fellow in the ocean section here in CGD. He received a PhD from the School of Ocean and Earth Science at the University of Southampton. And his research interests include large-scale physical oceanography, ocean modeling, predictability, and stochastic physics. His talk title today is Causal Attribution of North Atlantic Sector Variability Using Ocean Adjoint Models. So Dafydd, feel free to share your screen and take it away.
Okay, how's that?
Looks good.
Great. Okay, thanks Dan, and thanks everyone for tuning in. I'm going to use my time today to talk about some recent work I've been a part of, which aims to disentangle the variability in climate relevant quantities of the ocean. I'd just like to begin by thanking my PhD advisor, Florian Sevelek, who supervised me through a great portion of the amount of work I'm about to present. And also Dan, who's my postdoc advisor here at NCAR, and Luann Thompson at the University of Washington, who've both been working to take this in some really cool new directions, which I'll touch on at the end. Okay. So we know the ocean is a key player in climate changes on seasonal and longer timescales. And for example, it's often quoted that the ocean has taken up more than 90% of the excess heat associated with anthropogenic warming. And if we focus on that example for a moment, we might naively expect this to be a quite straightforward procedure where the heat goes in and the ocean heat content goes up. But of course, we know that the picture is a bit more complex than this. We have a large-scale ocean circulation which moves this heat around, and we know this circulation is subject to change. We know that at the mesoscale and below, the ocean is full of eddies, which are chaotic and unpredictable. And we know that at the surface, we have a highly turbulent atmosphere, which acts as a boundary condition. And so it follows that from these factors and many others, the increase in heat content isn't very smooth, and there are large variations on a range of timescales. And fluctuations like this are ubiquitous in the modern record for many quantities of the large-scale ocean circulation. So another common example is the Atlantic Meridional Overturning Circulation, or AMOC, which is a key component of the global meridional transport of heat. And based on sparse shipboard measurements over the last 40 years, a rather alarming decline became apparent in the AMOC, and even went as far as to inspire a well-known disaster movie that I won't name. But since 2004, the era of continuous AMOC observation has revealed that things are a bit more complicated and that these measurements lie within the bounds of natural variability. So a potential and predicted decline is much harder to tease out. So the question we'll be trying to address today is how do we quantify this variability and determine where it comes from? And I'll be trying to make the case for a novel approach which uses adjoint models of the ocean. And these are cheap to run, and they're based on causation rather than correlation. So variability is traced through the model physics back to its origins directly. But these models aren't very common and they're quite strange beasts. So I'll start by trying to build up some intuition for them before going into the results. So an ocean model typically describes the evolution of certain variables like temperature and salinity, which uniquely define the state of the ocean at a given time. And we can describe this unique state using a vector, which is just a long list of all of the values of these variables at all of the model grid points at that time. And so what we can say is that the model is numerically solving just a nonlinear function of this state and time. And to make this a bit more kind of visually graspable, here's a schematic representation of that. So on the x-axis here, we have every possible ocean state in January unraveled into one long line, which relates this to the evolved state down the line in June. So this is every possible outcome. So as a kind of more appealing example, here's a snapshot from a particular ocean state in January. And this just shows the sea surface temperature in the North Atlantic. And I'll ask for forgiveness on the colors for this plot because they are awful and the plot is older than I'll care to admit. But just as a visual kind of example of what's going on. So here's how that state evolves 6 months later. This is from the same model run, but in June rather than January. So this before and after pair corresponds to a single point on this curve, which we can mark here with a star. And so in order to build up a picture of what the full curve looks like, we would have to run the model over and over and over again with every possible input state in January to see how they evolve 6 months later. And obviously this is hugely impractical to do. But we know from school that we can just, draw a tangent line to this point. And we can get a fair idea of how the curve behaves nearby this point. So we can add a small change to our state in January, just shift it along slightly like this, and then see using our tangent linear approximation how this change evolves in June. And then from that, we can determine how this particular anomaly impacts quantities of interest down the line, like the ocean heat content or the AMOC or whatever it is that we're interested in. Okay, so this is really nice, but how do we get to it? Well, as with any tangent line to a curve, there are two requirements. We need the value of the point at which we're drawing the line. And as we saw in this model example, this is just what happens when we run the model once. And we also need the gradient at that point. And this is where things get a little bit more complicated. So in this kind of nice schematic example, this looks fairly straightforward. Our gradient is just a scalar value, a dy by dx sort of arrangement. But of course, for a full ocean model, things are a lot more complicated. Ocean models take huge vectors as input and output. And so the gradient is actually a matrix which contains millions and millions of entries. And in order to obtain this gradient, some poor soul has to go through the model's code and differentiate it line by line, find the differential of every operation with respect to every variable. And this is extremely non-trivial to do, but thankfully it has already been done for the two models I'm going to talk about today, and that's how we end up with these plots that I can use to demonstrate how things work. Okay, so once we have our tangent linear version of the model, we can take any specific anomaly like this one in this example and evolve it forward in time. And then we can estimate the impact on some quantity later on. And to make this a bit more mathematically concrete, we can say that we can represent our anomaly like the ocean state as a vector, just a long list of values. Here it's just 1 everywhere here and 0 everywhere here. And then we can also represent the evolved state of this anomaly using a vector. And so what we're doing is we're linearly transforming a vector into another vector. And so that means we can represent this tangent linear model using a matrix. Okay, and just one last thing to tack on the end of this, which is a touch more abstract. We can also represent the quantity that we're interested in using another vector. So here, for example, with heat content, we have another vector which acts on this vector to produce our heat content. So everywhere there's a temperature value, we multiply by the local volume and then add that to the total. And anywhere there's, say, for example, salinity, which doesn't contribute to heat content, we just throw that away. Okay, so this is a kind of mathematically dense way to describe something which is, I guess fairly obvious, and which doesn't give us anything really that new. In order to determine variability using this approach, we would need to sort of probe the system by applying lots of anomalies separately and then working out their impact on heat content later on. And we can do this just by running a normal model ensemble. So what's the advantage here? Well, if we take a step back and think about it, now we have all of this information, we don't need to do things this way around. We know that we're specifically interested in the heat content. And we also know, thanks to our gradient, that we have the rate of change of everything in the model with respect to everything else. So instead of just applying these perturbations one at a time and working out their value of heat content using this gradient information, we can just start with the heat content and say, using the gradient information, what is the rate of change of heat content with respect to any earlier perturbation in January? And this is what the adjoint of the model does. So whereas our forward tangent linear model takes a specific anomaly and evolves it forward in time, allowing us to estimate the impact on any quantity later on, the adjoint of the model restricts us to just one specific quantity that we're interested in, and then evolves it backward in time, but then gives us the ability to estimate the impact of any perturbation offline using the model output. Okay, so this is kind of an abstract idea, and it would be nice to have some sort of visual idea of what's going on alongside this. So let's start with an example. For our quantity that we're interested in, we'll now switch from heat content to the volume transport across a constant latitude line, the AMOC, across this line 55 north. So the quantity is just the amount of water that's being shifted over this line per unit of time. And if we feed this into our adjoint model, what we get back is this kind of unusual output, which is a map of sensitivities. And as I've said, once we have this output, we can apply any perturbation and determine the impact. So let's just take a typical anomaly, which we'd like to work out the impact of. And this is just a typical anomaly which results from surface forcing to the surface temperature. Okay, so we're going to project this thing onto this adjoint output and determine the output. And before we do so, let's see how well these sort of things match up, these two maps. We would expect that this would have quite a strong impact on our AMOC because it seems to do all of the right things in terms of the adjoint physics. It's cooling the Labrador Sea, it's warming along the west coast of Europe, and then cooling along the west coast of Africa. So it seems to be lighting up all the right areas in terms of what the adjoint wants to see. Albeit it's wasting some effort, for example, heating up the Gulf Stream, which the adjoint is telling us will achieve nothing. But when we apply these two, when we multiply these two maps together and sum over space, we get a 0.01 sphere drop change in the AMOC. And for any non-oceanographic viewers, a sphere drop is a unit of ocean volume transport, which roughly corresponds to 1 Empire State Building full of water per second. And a typical value for the AMOC is on the order of 10 to 20 sphere drops. So this is very, very small. Okay, so what's happened? Why isn't this working? As we've seen, this seems to be, ticking all the right boxes and not doing anything. But when we think about what we're doing here, it's actually kind of a weird thing to do. The ocean isn't being stimulated by a one-off instantaneous surface anomaly. It's being stimulated by a constantly evolving atmosphere. And we would expect it to have some sort of memory of that history of forcing. Okay, and additionally, if we're going back in time, these sensitivities are going to change as well. This isn't a fixed map. As we go further back in time, these become weaker and more spread out, which makes sense. If we were to apply a perturbation now, it will have much less impact 10 years from now than it will tomorrow, but it will also have the ability to travel farther. Okay, so it's hopefully not a huge leap of faith here to say that the accumulated impact of a history of forcing anomalies on our quantity of interest is given by convolving the time-changing sensitivities with these time-changing anomalies and then integrating through time. And this particular forcing history that we have here at the bottom goes from 1998 to 2018 and results in an AMOC anomaly of 0.65 sphere drops, which is a bit more realistic. But once we have this adjoint output, as I've said, we're free to apply any anomaly or any perturbation that we want. So we don't have to apply the specific forcing history from 1998 to 2018. We can apply a completely different one, which will produce a completely different value. And so we're interested in the variability of our quantity of interest. And so what we can say is that the variability in our quantity of interest, which is stimulated by this forcing, is the variance of all of the possible forcing values. So the result of applying many different forcing histories, calculating the impact, and then working out the variance of all of those different impacts. Okay, so we're now talking about variability, which means we're almost home, although I admit there's been quite a lot going on here. But there's just one last thing to say. So as we've said, we can apply many different forcing histories and then calculate the impact and then work out the variance of all of these different things. But we don't have to go through the tedium of doing that, because if we actually go through the maths and think about what's happening here, the only thing that's seemingly randomly varying is this forcing history. And so when everything shakes out, it turns out that it's sufficient just to know the covariance relationship of this forcing with itself. Once we have that, we can have a single equation which relates the variance in the forcing to the variance in our quantity of interest. So I've skipped over a lot of maths here, and I'll be honest, I've just flown through in 15 minutes what has taken me several years to wrap my head around. So I'll just try and make sure that everyone's on the same page by just summarizing what we've gone through, because this equation will now form kind of the backbone of the results of the presentation. So what we have here is a recipe for variability in any quantity of interest in the ocean. And this recipe needs just 3 ingredients. We need a vector which defines our quantity of interest. So in the previous example, the volume transport. We need a linearized ocean model and its adjoint. And then lastly, we need a covariance relationship of the forcing which is stimulating the variability. And we can get all of these things from just models and outputs and all this sort of thing. But what's powerful about this is we can split these different terms up. So for instance, we can split this forcing term into contributions by the wind or from surface heat fluxes. And then we can work out how important each of these different contributions are individually. And so this will be quite powerful in terms of attributing where the variability is coming from, both in space and from time and from different variables. We can unpack all of this using this equation and splitting it up. And the results I'll be showing are going to do just that. So as I've said, this equation is the kind of backbone of those results, and I'll make sure to leave it on screen pretty much as possible for the rest of the presentation. And we'll begin by returning to our opening example of heat content variability. So we considered that heat content is affected by the heat transport of the large-scale ocean circulation, but also that this circulation can be modified by anomalous heat content. So there's a feedback effect. And what we'd like to know is how important is this feedback effect for heat content variability? So to interpret that in terms of this recipe, what we'd like to do now is assess the importance of this feedback effect. And we can split the terms here which contain the model physics into a dynamical component which contains this feedback effect, and then a passive component which doesn't. And so what we're aiming to do is calculate the surface forced variability in heat content, and then determine how much of this variability is due to the dynamical response of the ocean and how much is just due to purely passive transport processes. To be a bit more concrete about this, in the passive component, there are only 2 ways that the heat content can change. It can be fluxed in at the surface and then passively transported by the mean circulation, or heat which was already present in the ocean can be redistributed by the existing wind. So heat which was here can be moved over here, et cetera, et cetera. And then we also have this dynamical component, which contains everything else. This contains the thermal wind response and things like this, for example, which relate changes in density of the ocean to changes in transport by the ocean. Okay. So before we dive into the results and see how much of this heat content variability is passive and how much is related to ocean dynamics, let's talk a bit more about the model setup, or where we'll be getting the 3 ingredients from. So our ocean model is NEMO, and we'll be using its linear counterpart NEMO-TAM in a 2-degree configuration. Now we can separate the model physics, as we discussed, using an on-off feedback switch, which we coded into the model in a previous study. This allows us to just turn this dynamical feedback effect on and off. And the nonlinear run, the point where we find our tangent line, this is forced using a repeated annual forcing package, core normal year forcing. And this ensures that the ocean dynamics are consistent from year to year, such that all of the variability in the outcome purely comes from this variability in the forcing that we apply. Okay, and this forcing was taken from a CMIP5 class coupled climate model, which we ran in a pre-industrial control configuration for 20 years. And from that, we took freshwater fluxes, and zonal and meridional wind stress. And I should remark also that the coupled climate model that we took this from uses NEMO as its ocean component. And so the grids between the two are the same, and we don't need to do any interpolation or anything like that. We can just take the outputs from one and apply them straight onto the other. Finally, our quantity of interest is heat content, as we've discussed. And I'll just present our results for the North Atlantic today, which we evaluated over 3 different depth ranges, and I'll elaborate on those in the next slide. So this is the region that we'll be looking at, and we're interested in heat content variability over 3 depth ranges, as I've said. So we're interested in the surface layer, or the top 10 meters, which effectively is just the top level of the model and corresponds to the sea surface temperature. And then we'll look at the upper ocean, or the top 1500 meters, and then the full water column in its entirety. And here's how the variability breaks down in heat content for each of those different depth ranges. In the surface layer, the overwhelming majority of the heat content variability is explained by the passive response to surface heat fluxes, that's shown here in red. Then we have a smaller contribution from the passive response to wind, and then a tiny minority which results from the ocean dynamical feedback component. When we move to the upper ocean over the top 1500 meters, we still have a majority of the variability that is stimulated by passive processes, but this is now much more evenly distributed. So we have a roughly even split between the dynamical component and the passive components, the wind and the surface flux component. And then when we move over to the full water column, the variability is predominantly the result of ocean dynamical feedbacks. And so in order to understand more about where these differences come from, we should take a look at how we arrive at them. These are just 3 numbers more or less that represent this, but in order to get to them, the ocean had to respond to time evolving forcing. So let's take a look at the time evolving growth of variability in response to this forcing. And here's how the variability evolves over time in each case. So for now, I'll just focus on the surface layer, and I'll just draw attention to these black lines. And the black dotted line here is the response over time for 60 years in the passive ocean, whereas the black solid line is just a kind of regular ocean which contains the passive transports, but also the dynamical feedback. So it's just what we usually expect from an ocean model. And unsurprisingly, given what we saw in the previous slide, these 2 lines are nearly coincident. We rapidly converge to a constant value, which is almost the same in both cases. But as we'd probably expect from these other 2 bar plots, things are a bit different when we move through the water column. Things start to change over the upper 1500 meters, and then the differences become particularly extreme for full depth heat content variability. So what we can see here is that in the passive ocean for the full depth, we have this initial growth which kind of levels off much as it does in the surface layer and in the upper 1500 meters. But then in the fully active ocean, there's this different response where we have an initial growth followed by a sort of stalling effect during the first 10 years. And then this is followed up over the next 50 years by an acceleration, which allows the ocean to overtake the passive response again. And so interestingly, this delay means that the half time of the variance growth, or the time taken to reach half of this final variance value, extends from just 3 years in a passive ocean to over 20 years in a fully active ocean. And this is interesting because this half time of variance growth, or the time of signal noise equivalent, is often taken as an estimate of the limit of predictability of a quantity. And so this implies that whatever dynamics are causing this early delay in growth are acting to hugely increase heat content predictability. relative to a passive ocean. So what we'd like to know is, where does this delay come from? Well, to see where this effect comes from, we should take a look at where the actual variability comes from. And for now, we'll just focus on the surface buoyancy flux component here in red, as this is where the difference is most pronounced. So during the first 10 years, when the dynamical component is slowing the growth of variability, this is a map of where the variability is coming from. So the shading here is the passive component, and the contours give the dynamical component. And what we can see is that this dynamical component corresponds to a large-scale dipole. And the negative end of this dipole is overlying what would otherwise be a positive contribution from the passive ocean. And so there's this sort of partial cancellation effect of destructive interference, which slows the growth of variability during the first 10 years. Now, what's different over the next 50 years is that this dipole evolves into a positive everywhere monopole. And so now we have a positive contribution by the passive ocean, which is bolstered by a positive contribution from the ocean dynamics. And so this acts to accelerate the growth. And these patterns and timescales, this dynamical contribution, they correspond to a mode of variability in our model in which AMOC dynamics and heat content anomalies feed back on each other. So just to conclude this section, we've seen that heat content variability at the surface of the North Atlantic is a purely passive response to surface heat and wind anomalies. But full depth heat content variability, on the other hand, results from a destructive interplay between the large-scale ocean dynamics and the passive response. And this delays the growth of variability and potentially extends the predictability of heat content out to decades. However, there is one aspect of the ocean dynamics which we haven't yet taken into account. So far, we've only looked at the large-scale ocean response to synoptic scale surface forcing, but we know that there is also intense chaotic variability at the oceanic mesoscale. So what we'd like to know is, to what extent do these smaller scale ocean fluctuations stimulate fluctuations in the large-scale ocean circulation? Now, from the perspective of our variance attribution recipe, we now want to separate this central forcing term into contributions from the atmosphere and contributions from internal anomalies at the ocean, which are unresolved by our 2-degree model. Now, the first of these contributions, as we've seen, is relatively straightforward to diagnose. We can just take it from a coupled version of our ocean model, which uses the same grid. The ocean internal contribution, however, is necessarily at the subgrid scale. And so diagnosing it will require a higher resolution model and also some gymnastics. So let's take a look at how we actually diagnose this component and then what it does. Okay, so let's pretend that this box is a grid cell in our lower resolution model, and that the shading is the value of some variable like temperature. Now, from the perspective of a higher resolution model, this single value is the average of many values at smaller scales. And so there'll be a corresponding set of anomalies. Now, of course, these anomalies will just average back out spatially to 0. But the same is also true of the other variables. So we can pretend that this one is the zonal velocity, for example. So while these anomalies might average out to 0 by themselves, their product might not. And so what we're left with is some large-scale impact, which results from the transport of anomalous small-scale buoyancy fluctuations by anomalous small-scale velocity fluctuations. And if we scale this up and apply this approach between our 2-degree model and a higher resolution quarter-degree model for temperature, salinity, and all of the velocity components, we obtain this map of flux variability. So here the usual suspects stick out. We have our western boundary currents here, the Zapiola Jaya, and also the Agulhas. And these are the areas where the subgrid fluctuations will most strongly stimulate a sensitivity map of the type we saw earlier. Okay, so that's the gymnastics done. What's the outcome? Well, we'll start with heat content, as it's what we've already been talking about up to now. We'll shift focus a little bit and look at the differences between the subtropical Atlantic and the subpolar Atlantic. We're also going to be interested in how this variance attribution changes on different timescales. So we'll begin here with month averaged heat content fluctuations. And so these panels show the growth of variability in response to 60 years of forcing. And as before, the green here represents the wind-forced variability, which is contributing very little in this case, and the red represents the surface buoyancy fluxes. However, additionally, we now have this blue component, which corresponds to the mesoscale eddy buoyancy fluxes, which we hadn't previously considered. And so what we can see is that in both regions, the majority of the variability is externally forced. And this is particularly pronounced in the subpolar region, where up to 70% of the month average heat content variability is forced at the surface, with then a minority due to mesoscale eddies. And this picture doesn't change much on longer timescales. The second and the third row here show the same behavior roughly for annually averaged and decadally averaged heat content variability, respectively. So at both locations in the subtropics and in the subpolar Atlantic, and for all timescales considered, surface buoyancy fluxes dominate the response. Eddies have a pronounced but smaller effect, and wind contributes very little. However, if we change our focus from heat content to a metric of the Atlantic meridional overturning circulation, the picture changes quite drastically. So this is now the volume transport at 25 north in the subtropical Atlantic. This is roughly the location of the rapid array, which is where we've been continuously monitoring these volume transports since 2004. And what we can see here is that on monthly timescales, the variability saturates quite rapidly and is predominantly wind forced, with a pretty substantial contribution from mesoscale eddies, but almost nothing from the surface buoyancy forcing. Now, on the other hand, on decadal timescales, the majority is coming from surface buoyancy forcing, with almost nothing from wind, and still quite a sizable chunk from mesoscale eddies. But this sizable chunk becomes the majority on the annual averaged AMOC, where eddies contribute up to 60% of the total variability. Now, another difference between AMOC and heat content is that when we move to the subpolar Atlantic, this time at 55 north, the picture changes again quite drastically. So as before, these high frequency month-to-month fluctuations are predominantly wind forced, and these lower frequency decadal variations are predominantly surface buoyancy forced. But now we can see that there is a very minor role for mesoscale eddies, which contribute only up to about 20% of the total variability. So to summarize this section, we've seen that we can represent eddy buoyancy fluxes at the subgrid scale by utilizing a form of Reynolds averaging between a low resolution and a high resolution model. And we've seen these small scale forcing anomalies can have a drastic impact on large scale metrics of the ocean, in particular the subtropical AMOC. However, in the subpolar region, eddies have much less of an effect, and surface forcing is dominating the variability. And so this provides a kind of nice segue into the current and future direction of this work. So I'll wrap up by talking about where we've been taking this next. So as we've seen, the ocean has a dynamical role to play in North Atlantic variability, but in the subpolar region, this variability is predominantly surface forced. And so the work we've been doing during my postdoc aims to answer whether certain surface forcing structures are dominating this subpolar variability. Now, the typical approach we would use to answer this question would be to unpack this surface forcing into its dominant structures using EOF analysis. And shown here are the leading EOFs of the surface heat flux from the ECHO state estimate as an example. But this approach produces structures which explain most of the variance in the forcing, but that don't care that we are particularly interested in stimulating AMOC variability. And so as a result, while these structures are optimal in terms of explaining the forcing variability, they aren't strictly the best at explaining the response variability. Now, a different approach starts at the opposite end of the problem and allows us to use the adjoint sensitivity fields themselves to tell us which forcing structures would be most effective at stimulating variability. But these only care about the fact that we are interested in stimulating the AMOC, for example, and so they don't reflect the nature of what actual forcing looks like. They're highly idealized and based on the model physics, and so they do a very good job of explaining AMOC variability, but a poor job of identifying where energy is distributed in actual surface forcing. So what we've been working on is producing a set of patterns which finds a middle ground and is able to explain variability in both the forcing and the response. And these are shown here. So these first two patterns are able to explain a comparable amount of forcing variability to the leading EOFs. but they are also able to explain more than 95% of these heat flux forced subpolar AMOC variability. Which is useful to us is that also that they have this kind of interpretable nature about them, right? And they bear a striking resemblance respectively to the North Atlantic Oscillation and this dipole pattern that we discussed earlier in the presentation. And so while these results are quite new, and so far we've just been looking at the heat flux component of the forcing, I think we're becoming increasingly confident in the maths behind all of this. And so we're excited to take a deep dive and would encourage everybody to watch this space for further updates. Okay, so just to conclude everything with a classic wall of text slide, in part one, we saw that an adjoint model combined with the statistics of forcing anomalies, for example, from the wind or heat fluxes, allows us to trace the variability in quantities of interest back to its origins via the model physics. And in part two, which was taken from a recent publication of ours in GRL, we saw that this model physics can be separated into a passive and dynamical component, and that surface layer heat content anomalies in the North Atlantic are predominantly the passive response to surface heat fluxes. That the role of the ocean dynamics increases as we move through the water column, and that for the full depth heat content variability, AMOC-related dynamics are interfering with the passive response, which slows the growth of heat content variability. And potentially, three, which was taken from our paper in the Journal of Climate, we saw that by separating the forcing component into a surface component and a subgrid component, Atlantic heat content variability is mostly due to surface buoyancy fluxes in both the subtropical and subpolar region, and also at all timescales that we considered. We saw that for AMOC variability, however, the variability changes from a wind-forced regime on monthly timescales to a surface buoyancy-forced regime on decadal timescales. And that there are differences between the subtropical and subpolar Atlantic, in particular that eddies have little influence on subpolar AMOC variability, but that they dominate on annual timescales in the subtropics. I'll also add that the methodology here, I've kind of raced through it, and it contains a lot of kind of technicalities and assumptions and things like that. And so anybody who's interested more in that kind of side of things, they're really thoroughly explained in this one of the two papers. And so I just concluded this talk by talking about recent work which suggests that surface forced subpolar AMOC variability can be explained with just a few patterns of forcing. And I'll just wrap this all up by adding that if you're in any way interested in setting up and running either of these adjoint models for yourself, and in some way I can help with that, then please feel free to reach out to any questions. Thanks.
Excellent. Thank you so much, Dafydd, for sharing that work. We have lots of time for questions, so folks can please feel free to either raise your hand or enter some questions in the chat if you would like me to read them aloud. Okay, I see there's a question from Justin in the chat. He says, Dafydd, nice talk. Can you also look at the impact of eddy variability on AMOC via repeated forcing cycles for a high-res ocean? Noting Steve Yeager has looked at this.
Yeah, I'm sorry, I'm not sure I understand the idea of using repeated forcing cycles here. Is there any chance I could ask to elaborate on that slightly?
Justin, are you able to unmute yourself and maybe rephrase?
Yeah, can you hear me?
Yes.
Yeah,
thanks.
hi.
Yeah, sorry. So we have a set of high resolution POP sea ice, and they're forced by 50 or 60 years of a forcing data set like JRA 55DO. And then that's repeated 4 or 5 times. So each cycle has the same forcing, but the eddy variability is different in the high resolution ocean model. So I just wondered, and I don't know if Steve is here, but whether you can also learn something from that approach.
Yeah, so I guess this is kind of presenting a different angle of attack on the whole problem, right? Yeah, so I think there are some advantages to what I've just kind of shown in terms of, computational ease and the fact that everything is nicely directly attributed through the physics, but there are also a lot of assumptions that have to be made. And I think that this serves more as a kind of supplement to these other approaches that show up in the literature. So there's also this kind of ensemble approach for diagnosing eddy forced variability that shows up a lot in this kind of like Ossiput project has put out a lot of papers on this, and also this kind of spectral decomposition angle. So yeah, I think this would probably more kind of help the whole greater picture of AMOC variability forced by eddies. But I'm not sure how it would, this is quite a rigid framework, what I've just presented, and I'm not sure how much it's kind of able to be adjusted in terms of other approaches.
Thank you.
Frank, go ahead.
Hey, Dafydd, I had a question about your last bullet point there about the mesoscale being a dominant source for annual timescale variability in AMOC. And I wonder if you could, if the results you have provide any insight into what the what is the structure of the AMOC variability the eddies are exciting at 24 north or whatever? Is it the large, somehow the eddies are modifying the large scale east-west pressure gradient and then accelerating the AMOC, or is there something particular in the Florida current that changes, or what is the adjoint reveal about that?
Yeah, so that's probably something I should have prepared some bonus slides for or something. I should have seen that question coming, but we do have maps of where all this variability comes from in the eddy forced component. And it is largely, as you describe, it's kind of stimulating this east-west density difference, particularly, the western boundary current is obviously being highly excited by this kind of stuff, and that just naturally stimulates a constantly changing east-west density gradient. But when we unpack the maps, I think it's more of a kind of brute force thing with these eddies, that they are imposing so much energy that it doesn't really matter where it's being placed. It's just having some sort of effect on these adjoint sensitivity maps. But they are particularly strong along the line of latitude that we're evaluating on the western boundary current.
Okay, thanks.
All right. There's a question from Joe in the chat. It says, very nice talk, Dafydd. Is it fair to say that the optimal forcing of AMOC are the leading singular vectors of the adjoint operators, and the second plot includes the covariance of the forcing?
Is that, sorry, was that question in the chat?
Yeah, it's in the chat.
And I think I've missed it. Oh yeah, sorry. Okay, the optimal forcing of AMOC. Yes, that is pretty much exactly what's happening. Basically, when this last slide that I showed, which has these three sets of patterns, they each correspond to more or less a singular value decomposition of some sort of matrix. For the EOFs, it's the force and covariance matrix. For the optimal patterns, it's this kind of adjoint matrix, as you described. And then in this last set, which takes information from both, we've managed to come up with a sort of matrix version, which incorporates the forcing and the adjoint sensitivities.
All right. There's a question from Kevin, reader, who says, nicely organized. Do you have a way of testing the limits of linearity assumption? That is, do the perturbations put the model into a state where the linearized state is significantly different from the non-linearly derived state?
Yeah, this is a great question. So I think this whole approach is based on the idea that we have a linearly stable system, which is being agitated by minor perturbations. That's the kind of, the whole thing hinges on that. And in terms of to what extent that's true, I think that's going to be quite hard to test in terms of this adjoint approach. It's normally quite easy to test the linearity assumption adjoint approach because you have a linear model and a nonlinear model together. But in this case, we are applying these forcing sets to the linear model, which isn't as easily done in the nonlinear version. We'd have to run some sort of higher resolution version of it. But my understanding is, just based on running like a quarter-degree adjoint model, is they are very, very sensitive to things like baroclinic instability and tend to blow up quite quickly. But we don't seem to see any sensitivity in the larger scale stuff to being shifted into a completely new regime just by these small scale eddy perturbations.
All right, thanks. Judith, I see your chat it seems like maybe there's missing a second part there. Oh, thank you.
It just
Judith
came in.
has a question. Yep, thanks. Judith asks, says, I'm wondering if fitting a linear inverse model would result in the same optimal forcing and response pattern. This would be a way to circumvent having to have an adjoint.
Yeah, so there has been some work on this in the past, I think. There are a few studies which use linear inverse models to kind of get around the idea of having to differentiate and get the adjoint of a model. There are also certain studies by the same authors that tend to look at these optimal forcing patterns. I can't remember if there are any papers which do both at the same time, but the general takeaway from it seems to be that this is a viable approach, but the linear inverse model is quite sensitive to assumptions you make when deriving it. Even certain parameters and things can result in a completely different linear inverse model. But I guess then we just end up with a sort of quantity over quality thing where you can obviously get a linear inverse version of pretty much any model. It's just with an adjoint, you're restricted to one that someone sat down and bothered doing the coding for, which takes a very long time.
Thanks.
Of course.
Great. At the risk of some insider trading, I guess I have a question. You focused here on the North Atlantic, which certainly the dynamically rich region has lots of timescales going on, but the methods seem very generic. I was wondering if you could comment on other parts of the ocean or other problems where you think these could be interesting tools to bring to bear.
Oh yeah, that's a great question. I admit I'm kind of tunnel visioned on the North Atlantic after 5 years of focusing exclusively on it, but I think I can throw some light on that because this GRL letter that we wrote looks at a bunch of different regions. So we split the world ocean in 7 and look at it, how this changes. And the reason I focused on the North Atlantic in particular today is because that's where these kind of interesting differences in the role of the AMOC and things show up. But there are quite rich differences where in some cases, for example, the passive component dominates over all depth ranges. For example, the Southern Ocean, just due to the huge amount of Ekman transport that is shifting heat in and out of the Southern Ocean. Even, the surface layer is like 97% passive. And then as you move to the full depth, it barely changes at all. So I think that's quite interesting. The Indian Ocean is not my specialty whatsoever, but that seemed to show some very interesting dynamics that were kind of the opposite of what we saw in the Atlantic, which would be, I'd throw out to anybody who wants to look at that a bit further. But yeah, I think there's a lot of different things to look at here. And there are also limitations which are stronger. For example, I would say our results in the tropical Pacific probably should be taken with a heavier grain of salt, as they are based on this idea of a decoupled ocean and looking at variability, for example.
Excellent, thank you. Not seeing any other questions, so let's thank our speaker again and look forward to seeing you all next week. Thanks a lot.
Thanks.